Welcome back to the Python DSA series. In this video, we're tackling one of the most powerful and versatile data structures in computer science, the graph. Beat graphs model relationships between things: social networks, roadmaps, the internet, task dependencies. Basically any time you have entities connected to each other. Beat will go from the very basics, all the way through BFS, DFS, shortest path algorithms, minimum spanning trees, and more. Beat. Let's get into it. A graph is formally defined as G equals V, E, a set of vertices and a set of edges. Beat, vertices, also called nodes, represent the entities. Edges represent the connections between them. Click. Now what makes graphs different from trees? Beat trees have a root, a strict parent-child hierarchy, and no cycles. Graphs have none of those constraints. Beat, there's no root, cycles are allowed, and vertices can connect in any pattern whatsoever. This makes graphs incredibly expressive. Beat, social networks. People are vertices, friendships are edges. Roadmaps, cities are vertices, roads are edges. The internet routers are vertices, links are edges. Package dependencies, neural networks, airline routes, all graphs. Beat, if your problem involves relationships between things, the graph is almost certainly the right model. Before we write any code, let's nail down the vocabulary. Beat, you'll encounter all of these terms constantly. Click. An edge is the connection between two vertices. If it has a direction, meaning you can only travel one way along it, it's a directed edge. Otherwise, it's undirected. If an edge carries a numeric value, like distance or cost, it's a weighted edge. Click. The degree of a vertex is simply how many edges are attached to it. In directed graphs, we split that into in-degree edges pointing in, and out-degree edges pointing out. Click. A path is a sequence of connected vertices. A cycle is a path that starts and ends at the same vertex. Beat, a connected graph means every vertex is reachable from every other. Click. Two terms that come up constantly in advanced algorithms. A DAG, directed acyclic graph, is a directed graph with absolutely no cycles. It's essential for topological sort. Beat, and sparse versus dense. A sparse graph has far fewer edges than the maximum possible, while a dense graph approaches that maximum. This distinction affects which algorithms and data structures you choose. Next, let's look at the four main graph types you'll encounter. Click. First, undirected graphs, edges go both ways. Think friendship networks or two-way roads. Click. Directed graphs or digraphs, edges have a specific direction. Web links, package dependencies, Twitter follows. Click. Weighted graphs, edges carry a cost or distance. Navigation maps, network bandwidth, anything where connections have different strengths or costs. Click. And DAGs, directed acyclic graphs. The no-cycle constraint makes them perfect for representing task scheduling, build systems, and course prerequisites. Beat, most real-world graphs combine these properties. A weighted directed graph is extremely common. How do you actually store a graph in memory? There are three main approaches. Click. The adjacency list maps each vertex to a list of its neighbors. Space is O of V plus E, proportional to the actual structure. This is by far the most common representation, especially for sparse graphs. Click. The adjacency matrix is a V by V grid, where each cell tells you whether an edge exists. The upside, checking if a specific edge exists, is O of 1. The downside, it always uses O of V squared space, even if most entries are 0. Click. The edge list is just a flat list of all edges as tuples. Space is O of E. It's used by specific algorithms like Kruskal's MST. Click. The comparison table makes the trade-offs clear. Beat. And the bottom line? Beat adjacency list is almost always the right choice. Unless you're doing dense matrix-style graph processing or need constant-time edge lookups, reach for the adjacency list. Let's build our reusable graph class in Python. Click. A constructor takes an optional directed flag, defaulting to false. Internally, we store the adjacency structure in _AJ, a plain dictionary. We also track _directed and _edge _count separately for convenience. Click. Add _vertex, simply ensures a key exists in the adjacency dict. Remove _vertex deletes it, and cleans up all incoming edges from every other vertex, O of V plus E in the worst case. Click. Add _edge is where the directed flag matters. If the graph is undirected, adding the edge U2 versus also adds the reverse, V to U, automatically maintaining symmetry. Each edge stores a weight, defaulting to 1. Click. The remaining methods, remove _edge, neighbors, has _edge, vertices, num _vertices, num _edges, are all thin wrappers around the internal dict. The _wrapper gives us a readable adjacency list view for debugging. This class will be the foundation for every algorithm in this video. Let's see it in action. Click. We build a 6-vertex undirected graph with 7 edges, A through F. After construction, num _vertices returns 6, num_edges returns 7. Beat neighbors, B, gives us A, D, and F, exactly the 3 vertices connected to B. Beat has _edge, A, D, returns false. There's no direct connection between A and D. We can also build a weighted directed graph, specifying weight as the third argument to add _edge. Click, and the from_dict convenience constructor lets you initialize a graph directly from an adjacency dictionary, handy for testing and examples. Next, BFS breadth first search explores all vertices at the current distance before moving farther away. Beat, think of it as dropping a stone in water. Ripples expand outward level by level. The key data structure is a queue, first in, first out. Click, the implementation uses Python's dequeue for O of 1 onQueue and dequeue. We start by adding the source to both the visited set and the queue. Beat, on each iteration we pop from the left, record the vertex, then push all unvisited neighbors. Beat, time complexity, O of v plus e. We visit every vertex and cross every edge exactly once. Click, the BFS_distances variant tracks how many hops each vertex is from the source. Beat, running BFS from A on our sample graph gives A, B, C, D, F, E. The distances, A is 0, B and C are 1 hop away, D and F are 2, E is 3. Click, the queue trace shows exactly why this works. A goes in, we process A, push B and C, process B, push D and F, process C, D and F already visited, skip. Process D, push E, process F, E already queued. Done. Beat, BFS guarantees the shortest hop count path in unweighted graphs. Next, DFS depth first search goes as deep as possible along each branch before backtracking. Where BFS spreads wide, DFS plunges deep. The natural data structure is a stack, or the call stack via recursion. Click, the recursive implementation is the most elegant. We pass a visited set and a result list. Mark the current vertex, then recurse into each unvisited neighbor. O of v plus e. Click. The iterative implementation avoids Python's recursion limit, critical for large graphs. We push to a stack, pop, check visited, then push all neighbors. Beat, note the use of reversed, to maintain the same traversal order as the recursive version. Click all_paths uses DFS with backtracking to enumerate every possible path between 2 vertices. We add the current vertex to the path, recurse, then remove it. Click, the comparison diagram tells the story clearly. BFS expands wide across levels, DFS tunnels deep. Beat, in terms of use cases, BFS for shortest path in unweighted graphs and finding connected components. DFS for topological sort, cycle detection, and exploring all paths. A connected component is a maximal set of vertices where every vertex is reachable from every other. If the whole graph is one giant component, it's a connected graph. Click, the algorithm is elegant. For each vertex not yet visited, run BFS or DFS from it that explores one entire component. Repeat until all vertices are covered. O of v plus e total. Click, our demo has a disconnected graph of 8 vertices. The algorithm correctly finds 3 components, A, B, C, D, E, and F, G, H, 3 separate islands. Click, one important caveat. This works for undirected graphs. For directed graphs, reachable is not symmetric, so we need a different concept. Strongly connected components, where every vertex can reach every other in both directions. Beat, the algorithms for that are Kosaraju's and Tarjan's, both O of v plus e, but they're covered separately. Next, detecting cycles is critical. It determines whether topological sort is valid, whether a graph is a DAG, and whether adding an edge in Kruskal's would create a cycle. The approach differs for undirected and directed graphs. Click, for undirected graphs, we use DFS with parent tracking. If we encounter a visited vertex that is not our parent, we've found a back edge, meaning there's a cycle. The parent check avoids false positives from the edge we just came from. Click, for directed graphs, parent tracking isn't enough. We need 3-color DFS. Each vertex is white, unvisited, gray, currently in the DFS stack, or black, fully processed. If during DFS we hit a gray neighbor, that means we've looped back into our current path. That's the definition of a cycle in a directed graph. Click, both methods are O of v plus e. The mermaid diagrams show visually what a back edge looks like in each case. Topological sort produces a linear ordering of a DAG's vertices, such that for every directed edge from U to V, U appears before V in the ordering. Beat, think. Given a set of tasks with prerequisites, what order do you tackle them? Click, Khan's algorithm uses in degrees. Start by computing how many incoming edges each vertex has. All vertices with 0 in degree have no prerequisites, they go into the queue first. We pop a vertex, add it to our result, then decrement the in degree of all its neighbors. Any neighbor that reaches 0 in degree gets in-queued. If we finish with fewer vertices than total, a cycle exists. Topological sort is impossible. O of V plus E. Click DFS post order is the alternative. Run DFS, but only add a vertex to the result stack after all its children have been processed. Reverse the stack for the final ordering. O of V plus E. Click the course prerequisites example makes this concrete. Maths and Python have no prerequisites. They come first. Linear algebra requires maths. ML requires both linear algebra and Python. Deep learning requires ML. Kahn's trace shows the n-degree values evolving step by step. Dijkstra's algorithm finds the shortest path from a single source to all reachable vertices, but only when all edge weights are non-negative. Click the strategy is greedy with a minute heap. We start with distance 0 at the source and infinity everywhere else. Repeatedly extract the vertex with the smallest tentative distance, then relax all its edges. If going through this vertex improves a neighbor's distance, update it and push the new distance vertex pair to the heap. Click Dijkstra returns two dictionaries, dist, the shortest distances, and previous, the predecessor map for path reconstruction. Beat reconstruct walks the previous map backwards to build the actual path. Click demo on our weighted directed graph. Distances from A, C is 2, B is 3, D is 6, E is 8. The path to D is A right pointing arrow, C right pointing arrow, B right pointing arrow, D, costing 6, not A right pointing arrow, B right pointing arrow, D directly. The heap expansion trace shows exactly when each vertex gets finalized. Click complexity, O of V plus E, log V, beat. The critical warning, Dijkstra fails on negative edge weights. It assumes once a vertex is popped from the heap, its distance is final. Negative edges break that assumption. For negative weights, use Bellman-Ford. Next, Bellman-Ford handles negative edge weights, something Dijkstra cannot. It also detects negative cycles, cycles whose total weight is negative, making shortest paths undefined. Click the algorithm relaxes every edge, V-1 times. Beat. Why V-1? Because the shortest path in a graph with V vertices uses at most V-1 edges. Each full pass guarantees we've found all shortest paths of length up to the pass number. Click. The implementation includes an early exit. If a full pass results in 0 relaxations, we've already converged. No need to continue. Beat. Then we do one more pass. If any distance still improves, we've found a negative cycle. Click demo with a negative edge C right pointing arrow B of weight -3. The final distances are A equals 0, C equals 2, B equals -1, D equals 2. That negative edge made B cheaper to reach via C than directly. Click the comparison table. Dijkstra is faster, O of V plus E log V, but can't handle negative weights. Bellman-Ford is O of VE, slower, but handles both negative weights and cycle detection. Use Dijkstra by default. Reach for Bellman-Ford when your graph has negative edges. Floyd-Warshall takes a different perspective entirely. It computes the shortest path between every pair of vertices simultaneously. Click the dynamic programming recurrence is elegant. Dist equals min, dist, dist, plus dist. For each intermediate vertex k, we ask, is going through k cheaper than the current best path from U to verses? We iterate k over every vertex, hence the triple nested loop, and O of V cubed complexity. Click initialization, 0 for self-distances, the direct edge weight for adjacent pairs, and infinity for everything else. Click the algorithm handles negative weights without issue. It just can't detect negative cycles automatically, though that can be checked by inspecting the diagonal. Click the master comparison table ties everything together. BFS for unweighted single source, Dijkstra for weighted single source without negative edges, Bellman-Ford for negative weights single source, and Floyd-Warshall when you need all pairs. Choose based on what your problem actually requires. Next, union find, also called disjoint set union or DSU, efficiently tracks which vertices belong to the same connected component. It's the backbone of Kruskal's MST algorithm and a powerful tool for cycle detection. Click. The union find class maintains a parent array. Initially, each vertex is its own parent, and a rank array for balancing. It also tracks the total number of components. Click find V, returns the root representative of V's component. The magic is path compression. On every find call, we flatten the tree by pointing all traversed nodes directly to the root. This keeps future lookups nearly instant. Click Union U, V, merges two components. Union by rank always attaches the smaller tree under the larger, keeping trees shallow. If U and verses are already in the same component, meaning find U equals find V, we return false, signaling a cycle. Click Demo, merge AB, then CD, then AC. Afterwards, connected BD returns true. They're in the same component, even though we never explicitly join them. The path compression diagram shows a deep chain collapsing to a flat star after a single find call. Beat, the practical complexity, O of alpha of n per operation. That's the inverse Ackermann function, effectively constant for any realistic graph size. Next, A minimum spanning tree connects all v vertices with exactly v-1 edges, at minimum total weight. No vertex is left out, no cycles exist, and the total cost is as low as possible. Kruskall's algorithm is beautifully simple. Sort all edges by weight, then greedily add each edge if it doesn't create a cycle. Union find is what makes the cycle check instant. O of E log E, dominated by the sort. Click the code, sort edges as weight UV tuples. Call UF union U, V. If it returns true, the edge is safe to add, no cycle. Append to MST and accumulate the cost. Stop early once we have v-1 edges. Click Demo on a 5-vertex graph. Edges are added in weight order. AB weight 1, BD weight 2, AC weight 3. Then comes BC weight 4, but B and C are already connected through A, so union find returns false and we skip it. Then CE weight 6, safe to add. Final MST cost, 12. Click the starred edge diagram, shows exactly which edges make the cut. Beat callout. Prims is the other MST algorithm. It grows the tree from a starting vertex, and it's generally preferred for dense graphs. Kruskall's is preferred for sparse graphs. Next. Prim's algorithm builds the MST by starting at a vertex and growing the tree one edge at a time, always choosing the cheapest edge that reaches an unvisited vertex. It uses a minute heap of candidate edges, ordered by weight, O of V plus E log V. Click the implementation. Initialize the heap with all edges from the start vertex. On each iteration, pop the minimum weight edge. If the destination is already visited, skip it. Otherwise, add it to the MST, mark the vertex visited, and push all its outgoing edges to unvisited neighbors. Click Demo, starting from A on the same 5-vertex graph. Step 1. Heap has AB1 and AC3. Step 2. Add AB1, push BD2 and BC4. Step 3. Add BD2, push CD5 and DE7. Step 4. Add AC3. Step 5. Add CE6. MST complete, same cost of 12. Click, the flowchart shows the visited frontier growing, step by step. Beat, same MST as Kruskall's, both algorithms are correct, they just arrive there differently. Choose Kruskall's when you have a well-defined edge list and a sparse graph. Choose Prims when working with dense graphs or adjacency list representations that grow the frontier naturally. A bipartite graph is one whose vertices can be split into exactly 2 groups, such that every edge connects a vertex in group 1 to a vertex in group 2, no edges within a group. Equivalently, a graph is bipartite if and only if it contains no odd-length cycles. Click the algorithm is BFS2 coloring. Assign color 0 to the start vertex. Every neighbor gets the opposite color, 1 minus the current color. If we ever encounter a neighbor that already has the same color as the current vertex, we've found an odd cycle. Not bipartite, return false. We wrap this in an outer loop over all vertices to handle disconnected graphs. O of V plus E. Click Demo, the graph A1, A2, B2, B3, C3. The coloring assigns A, B, C to group 0, and 1, 2, 3 to group 1. Every edge crosses groups, perfectly bipartite. Click the mermaid diagram, shows the 2 groups in distinct colors. Beat bipartite graphs appear naturally in matching problems. Job assignments, stable matching, network flow. Anywhere with a natural 2-sided structure. Many classic interview problems are really just graph problems in disguise, especially 2D grid problems. Click grid underscore BFS finds the minimum number of steps from a source cell to a destination in a grid of zeros and ones, where ones are walls. The grid is an implicit graph. We never build an adjacency structure, we just compute neighbors on the fly using the 4-direction deltas. Beat BFS guarantees the minimum step count. The visited set prevents revisiting cells. O of rows times columns. Click num underscore islands is the connected components problem on a grid. Each cell of 1 is a vertex. Adjacency is the 4 cardinal directions. Beat. The DFS flood fill marks visited cells in place by overwriting with hash, avoiding a separate visited set. Count the number of times you start a fresh DFS, that's the number of islands. Beat. Also O of rows times columns. Click the key insight. Whenever you see a grid problem asking about connected cells, paths, or regions, it's a graph problem. BFS for shortest paths, DFS for component counting. Next, let's consolidate all the complexity numbers. Click for representations. Adjacency list wins on space, O of V plus E. Adjacency matrix offers O of 1 edge existence checks, but wastes O of V squared space on sparse graphs. Edge list is compact at O of E but slow to query. Click for traversals. BFS and DFS are both universally O of V plus E time and O of V space. Topological sort via cons is the same. It's essentially BFS with extra bookkeeping. Click for shortest path. BFS works in O of V plus E, but only for unweighted graphs. Dijkstra is O of V plus E, log V fast, but no negative edges. Bellman-Ford is O of VE, handles negatives and cycle detection. Floyd-Warshall is O of V cubed, for all pairs. Click for MST. Kruskal's is O of V log E, sort dominated, best for sparse graphs. Prims with a heap is O of V plus E, log V, better for dense. Click and union find, O of alpha n per operation, which for all practical purposes is O of 1. Beat. Print this table out. These numbers should be instinctive. Next. This decision flowchart is your cheat sheet for algorithm selection. Click Start with your goal. Visiting all vertices? If unweighted, BFS or DFS. If you want shortest weighted path, Dijkstra or Bellman-Ford, depending on whether negative weights exist. Beat ordering tasks in a DAG? Topological sort, cons or DFS post order. Beat shortest path between all pairs? Floyd-Warshall. Beat connect all vertices at minimum cost? Kruskal's for sparse, Prims for dense. Beat component tracking or union queries. Union find. Beat cycle detection? DFS coloring for directed, DFS with parent check, or union find for undirected. Click the single most important habit. Before writing any code, identify what your graph problem is actually asking. Once you match it to one of these goals, the algorithm choice is almost mechanical. Let's look at the most common mistakes and their fixes. Click the worst bug you can write, BFS or DFS without a visited set. On a graph with cycles you'll loop forever. Always initialize your visited structure before the loop. Beat. Using a plain list as a BFS queue, q.pop, 0, is O of n, making your whole BFS O of n squared. Always use DSA from collections. Beat. Running Dijkstra on a graph with negative edges, you'll get silently wrong answers with no error. Know your edge weights before choosing an algorithm. Beat recursive DFS on large graphs. Python's default recursion limit is 1000. Deep graphs will raise a recursion error. Use iterative DFS for production code. Beat. Modifying a neighbor's list while iterating over it. That's a concurrent modification bug. Work on a copy or collect changes and apply them after. Click the best practices column mirrors all of this. Always use a visited set. DQA for BFS queues, heap queue for Dijkstra, iterative patterns for deep graphs, and default dict for clean adjacency list construction. And when you're building production graph code, not interviews, consider Network X. It handles all of this and more, including visualization and advanced algorithms. Let's bring it all together. Click the graph taxonomy. Undirected or directed, weighted or unweighted, cyclic or acyclic. DAGs are the special case at the intersection of directed and acyclic. They unlock topological sort. Click Core Representations. Adjacency list for sparse graphs. O of V plus E storage. O of degree lookup. Adjacency matrix for dense graphs. O of 1 lookup. Click traversals in one line. BFS uses a queue. DFS uses a stack or recursion. Click Algorithm to Application Mapping. BFS for shortest hops and connected components. DFS for topological sort, cycle detection, and SCCs. Dijkstra for weighted shortest path. Kruskal or Prim for MST. Union find as DSU support and Kruskal's backbone. Click a quick API snippet at right is pure reference code, BFS, iterative DFS, and Dijkstra, each in under 10 lines, using only standard library tools. Beat graphs are the language of relationships. Master these patterns, and you can model and solve almost any networked problem you encounter. Beat. Thanks for watching. The full code is linked in the description, and I'll see you in the next one. Next. That's graphs. From basic definitions through BFS and DFS, cycle detection, topological sort, Dijkstra, Bellman-Ford, Floyd-Warshall, union find, Kruskal's, Prims, bipartite checking, and grid patterns. Beat. If this video helped, smash that like button and subscribe. It genuinely helps the channel grow. Beat. Drop any questions in the comments, and I'll get back to them. Beat. Next up in the DSA series, we'll be putting these structures together to tackle real algorithm problems. Stay sharp. Next.